Hello, my name is Rustam Takhanov. I will present my paper, which is called Induced Problem for Fixed Template Constraint Satisfaction Problems. So first of all, let me define what is constraint satisfaction problem in the variable value language, which is the most common one. So constraint satisfaction problem is simply a problem in which we are given a finite number of variables, and there is also a domain, a finite domain in which our variables take their values. So we have to assign variables to their values. So actually which means that we have to find an assignment which is a mapping from the set of variables to the set D domain. And simultaneously, we need to satisfy a number of constraints. So each constraint is just a pair in which the first element is a tuple of variables, the second element is just a relation over the domain D. So we have to assign variables to their values in such a way so that for each such tuple, the assignment should be in the corresponding relation. So this is the common definition in the variable value language, but we're actually going to use slightly different definition, which is the so-called homomorphism problem. So in homomorphism formulation, we just given two finite relational structures, and we have to find a homomorphism from the first structure to the second one, so from A to B. So just a reminder that finite relational structure means a domain together with some number of relations on that domain. And of course, for a notion of a homomorphism to be defined, these two relation structures should be similar, which means that there is the arity of corresponding relations should be the same. So the homomorphism by definition is a mapping so that any tuple from the first relational structure, any tuple from a certain relation of the first relational structure should be mapped to some tuple of a relation from the second relational structure. And this problem is in general, of course, an NP-hard one. But there are different restrictions of that problem. The main kind of restriction is when the second relational structure, gamma, is fixed. So let's suppose that the second relational structure is some finite domain D together with some relations ρ1, etc. Okay, this second relational structure, if it is fixed, then it is called a template, or sometimes called fixed template. And then if the second structure is fixed, the first one, of course, an instance of that problem. Of course, we assume that all the relations are given by the list of tuples and then we are asked to find in the search version of the problem, we are asked to find a homomorphism from the given instance A to gamma, or in a decision problem, we are asked whether this homomorphism exists or not. So that's basically the search problem, CSP gamma, is a recognition problem. In that recognition problem, we have to recognize the language. This is the set of all instances, the set of all relational structures A that are homomorphic to gamma. So basically, this problem, when gamma is fixed, it's called fixed template constraint satisfaction problem or fixed template homomorphism problem. And of course, the complexity of that problem depends on the exact template gamma. And for some templates gamma, this problem will be NP-hard, like here given. So it's easy to see that for the Boolean domain D, we can define these relations that correspond to different clauses involving three literals. And then CSP to such a template gamma will be equivalent to 3 satisfiability problem, which is NP-hard problem. Or there are other examples of templates. For example, here are given some examples that correspond to tractable problems, homomorphism problems. For example, 2 satisfiability, Horn, 3 satisfiability, linear equations, modular P, directed unreachability, 2 coloring. Everything can be modeled as constraint satisfaction problem with a certain fixed template. And these are all tractable cases. And there is a famous conjecture, which is now no longer a conjecture, but a theorem, that actually the complexity of that homomorphism problem for fixed template gamma is either polynomially tractable or NP-hard. And there is a theorem that was proved in 2017 independently by Andrei Bulatov and Dmitry Zhuk, who proved that fact, though this conjecture was first formulated by Fedor Vardy in 1998. And what is interesting that this result of Andrei Bulatov and Dmitry Zhuk, it was a result of plenty of intermediate results, and all of them involving so-called algebraic approach to constraint satisfaction problem, which means that all tractable constraint languages or tractable fixed templates, it turns out that they are completely characterized by the in certain algebraic language by the so-called polymorphism. So basically, for a constraint language to be tractable, it should have certain symmetries. But instead of symmetries, we use the notion of polymorphism. What does it mean, polymorphism? Polymorphism is it's a function f. So suppose that we are given some theta, which is an array relation over some domain U, and f is some k-array operation on that domain U, which means that f is a mapping from U to the power of k to U. So then we say that f preserves that relation theta, or f is a polymorphism of theta, or theta is an invariant under f if the following is true. So whenever we take a matrix whose values, n times k matrix, whose values are from the set U, and we assume that columns of that matrix, this will be n vectors, right? And these are all elements from theta. Since theta is an array relation, we can take such a matrix so that their columns are from theta. And since the number of elements in each row is k, we can apply our function f to the rows of that matrix. And whenever we apply to such a matrix, to the rows of such a matrix, the function f, the result will be always some n vector from theta. If this is true, if for any such matrix this is true, then f is said to preserve theta, or f is a polymorphism of theta. So an example is, of course, this relation. So this is a relation which is just simply partial order on the Boolean domain, and it is easy to see that function on the Boolean domain preserves that partial order if and only if it is monotone, right? So this is just an example of, and it turns out that actually for any constraint language or for any fixed template, we can define a set of its polymorphisms. Polymorphisms, which means that polymorphism of any relation in gamma. So it turns out that polymorphism are exactly actually symmetries that define that make a certain constraint language tractable. So actually, the result of Bulatov and Zhuk was the following: that if constraint language gamma, a set of relations, or fixed template gamma has a certain kind of polymorphism, then gamma is tractable, or corresponding CSP gamma is tractable. Otherwise, it is NP-hard. So what does this algebraic approach to CSP teaches us? It teaches us that polymorphisms are fundamental concept that using which we can describe all tractable constraint languages, and not only that. Actually, polymorphism is just a general property of constraint language, and it's easy to see that actually, if the constraint language or preserves a certain polymorphism, then any constraint satisfaction problem with that constraint language will be preserved by that polymorphism. So basically, polymorphism is just a certain algebraic procedure using which we can, from existing solutions of constraint satisfaction problem, we can define new solutions of the same constraint satisfaction problem. So they're interesting by themselves. So therefore, we slightly generalize and define so-called induced constraint satisfaction problem. So what is induced constraint satisfaction problem? The induced constraint satisfaction problem is defined in the following way. Suppose that you are given domain, and suppose that you are given some relation, M array relation of that domain D. Before that, let's fix some set of algebras with the same signature over the same domain D. So let's denote it as B. So A sigma over sub D is just a set of all algebras that belongs to some signature. Actually, what does this mean? It means that in our collection of algebras that we specify B, all algebras should have the same signature, means that the number of operations in each algebra should be the same, and arities should be also fixed. So any algebra by definition is the domain together with some operations on that domain. And given any collection of algebras, any relation, M array relation over D, automatically induces an array relation over that collection B. How it induces? In the following way. So this is a definition. So basically, if rho is a subset of D to the power of M, then we can define all such tuples of algebras A1, A2, etc., AM, so that rho is a subalgebra of the Cartesian product of A1 times A2 times AM. What does this mean in simple words? In simple words, this means that here by Cartesian product, we of course of algebras, we understand standard definition of Cartesian product of algebras from universal algebra. So what does this mean? That rho is a subalgebra of A1 times etc. AM. It means that if you take an operation from those algebras, for example, the first operation from A1, from the first operation from A2, the first operation from AM, and you build this tuple of operations, then this tuple of operations element-wise preserve rho. This is what it means, that rho is a subalgebra of. And the same, of course, true for the second operation in A1, the second operation in A2, etc. So basically, all operations, corresponding operations in A1, etc., AM, they element-wise preserve relation rho. And all such tuples of algebras that satisfy this property, A1, etc., AM, they will be now elements of this rho superscript B. So basically, any collection of algebras B automatically define induce for any induce rho superscript B. Why this construction is interesting? Okay, let's first give an example of this construction. For example, let's D be Boolean domain 0, 1, and let's rho be all pairs of 0, 1s except for 1, 1. And we can fix a certain collection of algebras. For example, this simple case, let's consider only two fixed algebras. First is the algebra on the Boolean domain, which consists of only one operation, disjunction. The second, algebra with conjunction. So disjunction, D conjunction. So only two algebras. They are, of course, similar because in both algebras we have only one operation, which is binary operation. So then, what will be rho superscript B? Rho superscript B will be a pairs or consist of pairs of algebras from the previous set B, so that these pairs of algebras element-wise preserve rho. It is easy to see that all pairs conjunction, 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 disjunction, disjunction, conjunction, they're all going to preserve rho, except for disjunction, disjunction. Why? Disjunction, disjunction, it's easy to see that when you will apply disjunction, disjunction to two elements from rho 0, 1 and 1, 0, then disjunction, disjunction will result in 1, 1, which is not in rho. So that's why disjunction, disjunction does not element-wise preserve rho. But all the rest, it's easy to see that when you will apply it to, for example, 0, 1 and 1, 0, for example, when you will apply disjunction, conjunction, the result will be 1, 0, and it will be from rho. So basically, it's easy to see that in that example, rho B, rho superscript B look very much the same like rho with. So basically, you can identify 0 with conjunction, 1 with disjunction, and it will be almost the same thing as rho. So why this construction is interesting? The reason why this construction is interesting is that for any such fixed collection of algebras, since it induces for any rho superscript B, then any constraint language means any set of relations over D, you can, all relations induces rho superscript B, and this defines a constraint language over B. So if gamma is a constraint language over D, then gamma superscript B is a constraint language over set of collection of algebras B. And analogously, if gamma is a relational structure, fixed template over D, then gamma superscript B that consists of the domain B together with relations rho1 superscript B, rho S superscript B, this will be a relational structure over B. And since it is also a relational structure, why not to consider constraint satisfaction problem with that new relational structure, gamma superscript B? And the interesting phenomenon that we observe is that for many interesting collection of algebras, this gamma superscript B will be tractable for any, even if initial gamma is NP hat. Let's give examples. For example, if B is all algebras that DB, where B is commutative and conservative binary operation over D. So commutative means B of xy is equal to B of yx, right? And B of xy, conservativity means that B of xy is either x or y, or any xy. So any so if we define such a set of operations, they're all similar again. And then this set of operation, of course, defines gamma superscript B. So for any constraint language, we can build a new language, gamma superscript B over B. And the interesting phenomenon that this gamma superscript B, it doesn't matter what kind of gamma we have, even if it is NP hat. Gamma superscript B will always contain one specific polymorphism. This polymorphism can be constructed directly in the following way, that if you are given three algebras, D, B1, B2, B3, then you can build from these three algebras the fourth algebra, which is just a superposition of B1 with B2 and B3. And using this, it is easy to see that this new algebra will be also commutative and conservative binary operation. So this basically a mapping from B to the power of 3 to the B. So this will be an operation on the set of all algebras B. And this mapping will be a majority operation. It will satisfy this relation. And moreover, it is easy to see that this mapping will be a polymorphism of any relation rho superscript B for any rho. So any induced relation rho superscript B will be preserved by this operation. So what does this mean? The majority operation will be preserved by any gamma superscript B. And this automatically gives us that gamma superscript B will be tractable because all languages with majority operation are always tractable, right? And this is not the only example. There are other examples of the same kind. For example, on the Boolean domain, we can define all weak Muir unanimity operations as a set of algebras. And again, for that set of algebras, we can define this four-array polymorphism. And this four-array polymorphism will make any gamma superscript B tractable. It will be a polymorphism of any gamma superscript B, and it always will be tractable. So this is the basic idea of our constraint. Gamma superscript B, if B, the collection of algebra, is properly chosen, selected, then gamma superscript B will be tractable for any, even NP hat gamma. Okay, what does it give us for our initial constraint satisfaction problem with the fixed template gamma? So in a constraint satisfaction problem with fixed template gamma, our goal is to find a homomorphism from some instance R to the fixed template gamma. And sometimes, of course, gamma could be NP hat, so it could be hard to find such a mapping from R to gamma. But suppose that we define B, collection of algebras, in such a way that gamma superscript B is tractable. So then we can always find homomorphism from R to gamma superscript B. Or such homomorphism, of course, may not exist. If it does not, if this homomorphism does not exist, then we cannot do anything in that situation. Then we are still cannot solve the problem. But suppose that we are able to find some homomorphism from R to gamma superscript B. This simultaneously give us the reformulation of our initial problem. So our goal was to find a homomorphism from R to gamma, but now, besides a relational structure R, we are also additionally given a homomorphism that we just found from R to gamma superscript B. So this is another problem, which is called CSP with an input prototype. So CSP with an input prototype is the following problem, that we are given a homomorphism from R to some fixed relational structure, but our goal is to find a homomorphism from R to another, so to a fixed template. So here we are given a homomorphism from R to gamma superscript B, and our goal is to find a homomorphism from R to gamma. And it turns out that this problem could be sometimes easier than CSP gamma. In fact, we prove the following statement, that if suppose that our collection of algebras B that we just specified, it consists of only tractable algebras. So a tractable algebra is an algebra whose set of invariants will be a tractable language. So suppose that all algebras in the collection B are tractable. Then we prove the following statement, that if the set B consists of only tractable algebras, then our problem of finding a homomorphism from R to gamma given a homomorphism from R to gamma superscript B will be also tractable. So what does this mean? It means that if our collection of algebras B was chosen in such a way that gamma superscript B is always tractable, and moreover, if in our collection of algebra B all algebras are themselves tractable, then we can apply the following strategy to solve initial CSP gamma problem. We can first find a homomorphism from R to gamma superscript B, and then using that structure, we can find a homomorphism efficiently. We can find a homomorphism from R to gamma. So this is basically our key result. So this theorem that if algebra set of algebras B consists of only tractable algebras, then we can find homomorphism from R to gamma, given a homomorphism from R to gamma superscript B. So besides that, we give some other theorems, other results, but this is the key idea. So this automatically defines plenty of different algorithms for CSP gamma. Of course, these are all algorithms that can lead to success only on the condition that at first stage, when you basically substitute gamma with gamma superscript B, the homomorphism from R to gamma superscript B exists. If it exists, then we can solve our initial problem, CSP gamma. Thank you very much for listening. This is the end. I can only add to that this whole formalism can be also applied to valued constraint satisfaction problem, and it could be made practical. Thanks.